So now we understood segmentation conceptually. Let us make it visible through a program. First, remember this, like we saw, operating system divides a program into segments like code, data, stack, and heap. Even though we cannot directly see segments, but we can definitely observe them through variables and memory addresses. Let us make this simple by considering a simple C program, which I will be writing. So, X dot C. So here, what I'm going to do is I'm going to declare different variables, and you will realize what exactly is happening. So, as include studio.h, as include stdio.h. Let us declare a global variable, integer global variable. I will give name like a value to it as 10 with initialize. Let me declare a function, word function. Okay, then its body. So we'll declare our local variable. Then we'll include some dynamic variable as well as a local one. So dynamic memory for heap segment. Okay, so integer star heap var. Now let us like get memory for it. Like sorry, instead of this, what we'll do is we'll allocate memory for it as it is a type of integer. So are we using malloc? Size of integer. Then I'm assigning value to this variable as heap var equal to some other value, 30. Now let us print using printf. I'll print the values like inside function. Correct. Printf address of local variable. So I will directly take name of it instead of writing local variable, local var. Okay, which is on stack. We know that local variable goes into stack. So %b so as to print that address. Fine. So now if we see like I'm writing this as a print %b then /n. Okay, then my address or variable of that I used in local var. Correct. So as we want to print address, that's why we are using it. Similarly, we'll print address of heap var. Is %b. Now, as we already have it as a pointer, so we need to write this var it as just for consistency purpose. Not it is not going to make any difference that way. And once done, like whenever you allocate a dynamic memory, you should make sure that you free it. Correct. Fine. Then your function is done. Now we have to write main and we will declare some static variable which would be for data segment. So here main. So I will declare static variable, static integer, static variable, static variable equal to, now I am taking another value so that we can differentiate between the values. And now like I will be using printf again. Okay. the way that we saw, we will write in main here too. Slash and double quotes. Fine. Then we have to print values for data code segment. So let us first print value for code segment as get printf. Sorry. Yes. Address of function. That is your code, correct? Which we wrote earlier. So again, we'll print %p /n and then function. Right. Then we'll print data section. So now we had a global variable above. Correct. We'll use global variable as well as the static variable. So printf address of variable. This is from data section. Correct. I will write like the way that we wrote for a data stack, code stack and thing. So enter, I will be doing same thing for data too. %p /n double quotes. Now address of global variable. Correct. Now, similarly, this is to be done for our static variable. Static var and here also we'll print static var. Correct. And then like we wrote the function, we'll give call to that function. Let's see and then return C. Get compiled. So let us save this and now let us compile. If there are errors, we'll try to correct if at all. Fine. Now, like if you see what I did here, so this there would be code segment. Okay, like if I really see, we saw two things are there. We wrote two functions. One is main, other one is function. Correct. Name of the function itself is function. So when we print address, like using printf, for example, for function, okay, this belongs to code segment. Then data segment, the global and static variable goes. These exist throughout the program execution. Okay. Stack segment, local variables, function calls, like your local var, correct? That would be there. So created, this is created, stack segment is created when a function is called, and it is destroyed when function returns. Fine. There is heap segment, like a dynamically allocated memory, like we allocated memory using malloc. Fine. Using malloc, yes. And then it is controlled by our you, like as a programmer, and it exists until explicitly freed. So that's why we wrote this free statement or free call. Then now when we execute this, let us execute this code. So which we created as executable. Now you will notice address are not random. Correct? They are grouped in this case. Like for example, code, check the address. It is different. Then data, then heap. Okay, then stack. Correct? Stack, heap. Okay, so I should modify this. I wrote here stack. This should be from heap. Fine. So let us go back. Let us compile again. Let us execute. Now you will see, like if you execute it again, most of the addresses are same, like almost all. So this shows the memory is logically divided. So even though we wrote the one program, the OS did not treat it as one block. So it is divided into meaningful segments. And so what we are seeing is segmentation in action. Now think like this as a system designer. Why should you separate them? Code, that is protected, which is read-only. Data, it is persistent. Stack, fast and temporary, and heap is flexible. So each segment has different role there. That is exactly what segmentation is, logical division based on the purpose. So we have not just written the code, we have observed how OS sees our program, one program and multiple segments, each with its own identity. Now, if at all, like for example, what we saw, we conceptually understood segmentation. Now we wrote the program, correct, through the mechanism. So here OS is not hiding everything. Linux provides tools which allows us to inspect how the program is laid out in memory. Let me first write this size, size command. Okay, when we created an executable, so I can write here dot slash a dot out. You can see the size. Output meaning text, which contains code segment, data, initialized data, and BSS, uninitialized data. So by default, probably it would take one thing. So this tells us how much space each segment occupies. Code, data, BSS. Already segmentation is visible. Now, if I go with objdump, say for example, and if I write dash h, my program them. So let us use this. Now we are going into deeper. Okay, you will see now sections like text, data, BSS, and so on here. Correct? If you go below, you can definitely see this text. There is read-only data. All these sections are added there, like data, BSS, and so on. So this segmentation is at binary level. Correct? What we saw. Similarly, like if you see when I write nm, okay, so nm and my program name. So these are rather, if you see, this shows where variables and functions are located. So for example, if I go and check for the data, okay, uh, let us see what variables that we had. We are using malloc, okay, which is uninitialized. Printf is not used, or printf is uninitialized. Then we see, let us see static variable. So it is showing us this 00400C. And when we executed, correct, for that static variable, check this address. Okay, so this compilation time or before execution, after compilation time, and this is after linking or runtime. What is the address? Now, if you see, there are different sections added. Each symbol belongs to the segment. Like if you see over here, like T, U means undefined, capital T means text section, small d, capital D are meaning for data section, and so on. So one can easily observe this like through other mechanisms too. For example, if I write dot slash dot out and ampersand, if I send it into background, correct, and then I am seeing PS AUX grep program. So if it is okay, then I am writing here my a dot out. Now, if you see, my a dot out is not executing currently because we have that is not in memory. Fine. So let me add something over here. Say wait for a while. So I will write here sleep 20. Okay. We'll use sleep function to or rather 10, and then we'll write here sleep 5. Okay, let us save this, and you may have to include header files as include ready. Let us compile. Let us write this. If you see here, it is showing us this out, correct? That the process is running. Now, if I write cat slash, hopefully that program is not completed. Okay, or otherwise we'll try one more time slash. Now PID, if I take 8524, and if I write maps, the code must have been executed completely. Right here, 8537. Now you can see all these sections like stack is shown, okay, with the address. Fine. then ultimately, like if you go with, you would be seeing different parts there. Now, what we are saying is here the live memory segmentation. You will see code region, correct? You will see stack, you will see shared libraries. These all are shared libraries, correct? This is the heap address that it is saying, correct? Then your executable name, all details are added here according to the even stack is there. Fine. So this is not theory anymore. This is your program running inside the segmented memory. Now let me execute again. I assume this is not available now. It is terminated. So let us execute this again. Then we'll write this. Okay, and then let me write pmap and PID. So 8564, 8564. You would be seeing again this another output. Correct. Here, this gives you clean summary of memory layout. How exactly the things are. Correct. So these commands will give you different ideas. So what we saw, we wrote a C program, we compiled it, then we executed that program. Then using size, we saw the segments. Using objdump, we saw the sections. And using proc, PID, maps, we saw runtime layout. So static view as well as runtime view, that's what results to your complete understanding. Now, segmentation is not imaginary. Please understand this. It is physically implemented and observable. So you wrote one program, Linux turned it into multiple segments, and you just saw it happening live. Okay. Thank you very much.